So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Weiyuan Gong, who will tell us about the sample complexity of purity and inner product estimation. So Weiyuan is a second-year PhD student at Harvard, and he's working with Professor Sitan Chen. He is primarily interested in quantum learning theory, quantum complexity, and quantum information. And before going to Harvard, he did his undergraduate at IIIS in Tsinghua University. So Wei-Yan, the floor is yours.
Okay, thank you so much, and thanks everyone for coming. So today I'm going to share our recent work on sample complexity of purity and inner product estimation with everyone. And you can check the archive version for this paper using this link. So this is a joint work with Jonas, a postdoc at Harvard. Qi and Zhihan, just as I mentioned, are graduate student and undergrad at Tsinghua University. So we start with the motivation of this work, and for this work, I will focus more on the high level intuitions and also some related works, and then about a little technical details about how we prove our results. So we start with the motivation. The first one is from an algorithmic perspective, from a theorist perspective. So as theorists in quantum information, I think one of the most core problems is to find some tasks that we can get some so-called quantum advantage. And you can see this is a figure just drawn from the Willow advertisement from Google team, and they kind of give different metric for evaluating different tasks that we might have some quantum advantage. You can judge them by whether they are difficult for classical counterparts or whether they are useful in practice. These are different methods to evaluate them. And for example, the new Google experiment, they use random circuit sampling, and it's also a well-known task that is provably hard for classical computers, but it is useless in practice. And factoring is another example that is extremely useful. Compared to all the quantum applications we know is extremely useful in practice, and we believe based on some complexity assumption, it is classically hard, but it is not available on near-term quantum devices unless we can have some quantum error correction techniques. So now at my side, I'm mainly working on the task for learning from quantum data, where we believe there will be some quantum advantage compared to the classical counterparts. The statistical advantage brought by learning quantum data quantumly compared to learning quantum data classically. I will elaborate more about this later. And also, learning quantum data has some motivation from the physics side. For example, you have a quantum system, and we want to benchmark the quantum systems. For example, judging whether the undergoing process on the quantum system is really quantum, or we want to make some predictions on an unknown quantum system. To do this, we have to basically just estimate some observables, or try to predict the probability distributions for some measurements, and this is from the experimental side. We want to predict or learn information from a quantum system, and from a complexity side, we believe that we can obtain some statistical advantage for learning quantum data quantumly. And this work is just another example on the complexity and potential information theoretical advantage in learning from quantum data. And another kind of motivation for this work is from what we can do based on our experimental devices. So just in the last week, we have heard several exciting news from different platforms. The upper figure is the quantum device from Harvard. It's a Rydberg atom device. They can do several hundred physical qubits, and like I think last week they showed that they can perform some kind of like early stage magic state distillation. And the lower figure is it's just a Willow quantum chip from Google AI. And the reason advancing near-term quantum devices just enable us to do some early stage quantum error correction. And it also provide us with more quantum qubits to have very limited quantum control. But like it's just because this very limited quantum control, we can learn quantum data quantumly to get some potential information theoretical advantage. The figure at the most on the right the side is the figure also from the Rydberg atom paper, where they try to benchmark their quantum state prepare on this Rydberg atom platform. And how they benchmark is through this logical entanglement entropy to see how well they prepare the state. And this entanglement entropy is evaluated by the Renyi entropy. And actually, like what we are going to talk about today, purity is a key subroutine for estimating the Renyi entanglement entropy. So these 2 points here just motivate why we need to learn from quantum data. The first one is like you have a quantum computer, we prepare some state or prepare some quantum dynamics. We want to see like how well we prepare the state. So we need to learn from the quantum data to provide feedbacks for further error correction or to like evaluate how we do error correction or mitigation. And a second perspective is because we can have more qubits to have very limited quantum control, so we can use this quantum control to get the information theoretical advantage we just claimed. Okay, now let's formally define or like describe learning from quantum data. So very generally, you just consider you are a learner and you are given n copies of unknown quantum state rho. The goal is to learn some properties of rho. For example, like you have some observables and you want to estimate the expectation value of this unknown quantum state rho for these observables without like fully do state tomography on rho. Like we don't want to like do some resource inefficient task like full tomography to get the full information of rho. We only want to know the observables. And similarly, just we want to know the purity of rho, or we want to estimate the entropy of rho using as little as possible, as little resource as possible. So the most standard, like from a theory perspective, I should say, because I have actually chat with several experimentalists, and there are even more fundamental setting. So I mean, from a theorist perspective, like the most practical but weak model here is the unentangled measurement. But yes, just as I said, like in experiments, the measurements are even weaker than like unentangled measurement. But here we just focus on this. So so in this setting, so every time we just prepare a fresh copy of rho, and we do a single copy measurement, and we collect the yeah.
Sorry for the interruption. I'm just curious, like, what can be weaker than an unentangled measurement?
Oh, you can do like single qubit measurement, like computational basis.
Oh, okay, that's what you're
right.
Okay.
Yes.
Okay. Okay.
I think actually, like in most experiment setting, arbitrary single copy measurement is still like beyond what they can do.
I see. I understand. Okay, thank you.
Yeah. So I believe there can be like some recent work on showing like the power of like single qubit measurement, even weaker model of single qubit measurement. Yeah, but like up to now from the theory side, the unentangled measurement setting just practical and weak, just as said. And you just prepare rho at each time and measure it, and you collect the classical data and do classical data post-processing. And the strongest model is like you can do arbitrary joint measurement. Means that you can prepare arbitrary M copies together in parallel and then measure them also in parallel. So this is also known as entangled measurement. There are many like measurement restrictions in between, and one of is like the measure you can measure, but you have only bounded quantum memory. We will elaborate a little more about this later. And because we are learning from quantum data, so one more key factor is the so-called adaptivity, which means like you learn based on what you have. So that is like a learn. For example, in the unentangled measure setting, you measure a first copy of row and you get some particular output, and then you prepare a next copy of row. And based on the previous history, based on the previous outcome, you can decide how to measure the next copy. And this is known as the adaptivity. Okay, let's talk a little bit more about learning with quantum memory. So as shown in this figure, we can just imagine learning with quantum memory as something like you have a quantum analog of the memory in your laptop. So here it's like you have n working qubits and you have k qubits of quantum memory, and at the beginning of each at the beginning of each round, you just initialize your quantum memory. Here we assume k is smaller than n, but actually k can be arbitrary value. So you initialize your quantum memory, and then you input a row, and you together with the working qubit, you can perform a joint measurement on all n plus k qubit, and after the measurement, you will write the data into the quantum memory, but the quantum memory is limited size. It only has k qubits. And then you input another row in the working qubits, and you perform a joint measurement on n plus k qubits, and and after measure you again just write some data to the quantum memory, and so on. And we assume that the learner can sequentially query C copies in this setting, which means if you regard this stuff as a circuit, then the circuit depth is C. Okay, and in the most general case, C can be any number, like it can be infinite, but although it is not practical. So we actually don't know the power of general like bounded quantum memory protocols. Like if you allow C to be infinite, we don't know its relationship with like single copy measurement or two copy measurement. But at least we can see if we only have C equals to 2, which means the circuit depth can be only 2, then this case, it should be strictly between single copy and two copy measurement. Okay, before we show more results and like go into our problem, I can show you some examples for why we can get information theoretical advantage from learning quantum data using quantum memory. And that is what I said before, learning quantum data quantumly. So in generally, we can say like if you learning quantum data classically, then you are just doing something like unentangled measurement. You query the quantum data, get classical output, and then do classical data processing. But if you learn quantum data quantumly, then you can get some kind of like quantum control, and you can do quantum data post-processing. And there are several examples where we can see exponential statistical separations with and without quantum memory. The first example is the well-known shadow tomography. The shadow tomography is a task where you have an unknown quantum state, and you have m observables, and you want to estimate the observables without even like knowing what exactly the unknown quantum state is. So it is shown that if you can do only single copy measurement, which means you do single copy measurement and do classical data processing, then the sample complexity here is tight. It is a minimal in m, which is the number of observables, and 2 to the n. It is the dimension of the quantum state. And this is just the well-known classical shadow result from Huang, Keong, and Priskill in 2021. But according to Scott Aronson, Badescu, and O'Donnell, this series of work, if you only consider like 2 copy POVMs as the as the stuff you want to learn, and if you allow joint measurement on log square m copies, which means that the quantum memory is like log square m times n qubits, then you can achieve n times log square m. So you have an exponential separation between you have full quantum memory and you can only do unentangled measurement. Similar things also happen for purity testing. So purity testing is a test where you have where you are dealing with a distinguishing task. In case one, you have some high random pure state, and in case two, you have maximum mixed state, and you want to distinguish which is the case. So for answer-free protocols, it is proved that square root d, or 2 to the n over 2 copies of samples are necessary. But if you have 2 copy measurement, then you can simply just do swap test. And swap test has no dependence on n. You only need you only need constant number of copies. A similar task here is distinguishing unitaries. It's like you have an unknown black box oracle, and in the first case, the oracle is a fixed unitary, while in the second case, it outputs different high random unitary. So this work is from Mahanarov, Kotler, and Qi in 2021. They show that for any answer-free protocols that query this unknown black box, you will need like omega. Anyway, it's an exponential number of queries to distinguish between these two cases. But again, if you have 2 copy measurement, what do you need is swap test again. And a recent work also shows this separations in polychannel eigenvalue estimation. So all the three examples I mentioned above, you will need at least like n qubits of quantum memory to achieve exponential statistical advantage. But here, we show that with only log n ancillary qubits or log n quantum memory, you can achieve an exponential reduction in the number of measurements you need to learn the eigenvalue for an unknown polychannel. Okay, so let's go back to our work. As we mentioned in the title, there's the inner product estimation, and that has something to do with learning quantum data in a distributed case. So in a distributed case, it's different from what we just talked about, learning locally. Here you have 2 people, and for example, Alice and Bob, and they're given n copies of unknown quantum state rho and sigma at each side. And their goal is to learn some function related to rho and sigma. For example, the inner product of rho and sigma, or some observables acting on rho and sigma. And of course, we cannot assume Alice and Bob have arbitrary communication. A very standard setting is that they only have classical message between. So it's like LOCC in what we have learned in quantum information lectures. And another setting, which is considering our work, is that Alice and Bob can have some kind of restricted quantum communication. So for example, we restrict their communication to be like k-qubits. But there are also 2 ways to define this k-qubit here. The first version is that Alice can prepare 1 copy of rho at a time, and Bob can also prepare a copy of sigma at a time. And for each round of state preparation, I mean, for each copy pair, they can share k-qubit. So it's a lower line, and which means that for every which means they have a k-qubit quantum channel, and every time when they prepare 1 rho and 1 sigma at the side, they can exchange k-qubits. And this is considering our work. And another setting is like they can interchange at most k-qubits in total. The second case is like Alice and Bob have a lot of samples at their side, but they have very limited quantum communication, and they can only share k-qubits in total, not for each pair. So in this work, we just focus on the later one. But I will also mention some concurrent work with our work. They consider the first setting. Okay, we give a formal definition for purity estimation. For purity estimation, it's just based on learning from quantum data template. You are given unknown quantum state rho, and the goal is to estimate trace rho square to accuracy epsilon.
Sorry, just to clarify. So it's for the qubit channel, the k-qubit channel. So this you allow it in both directions. This is not like one direction.
Yeah, for general case, you should allow arbitrary arbitrary directions, but our work only show this for one-way, so for one-way communication.
Okay.
Yeah.
Okay, thanks.
So the task is just to estimate trace row square to accuracy epsilon. And there are several applications for this. The first one is just I mentioned at the very beginning when we talk about motivation, is when we want to estimate the entanglement entropy, specifically the entanglement ring entropy. It is defined as this. So you can see when alpha equals to 2, and this is actually the metric considering many like experimental papers. And then you should first estimate purity to estimate the entanglement entropy. And also, just as we mentioned, if you prepare a pure state, you want to evaluate, okay, because there are noise on the circuit, we want to evaluate how good we prepare this state. Then we just have to do purity estimation. And also, just I mentioned, it's a testback for quantum sample memory trade-off. And another test considered in this paper is the distributed version of inner product estimation, where Alice and Bob are just to estimate trace row sigma, the inner product. And this also has some motivations here. So the first one is this task just directly originates from this cross-platform verification. Where it's just like you have two quantum computers. They can be totally different platform. Like Alice is performing some superconducting quantum computer, and she prepare row, and Bob is operating something like a ion trap quantum computer, and he prepares sigma, and they have only classical message, or they can send they only have a like limited quantum channel, and they want to they want to like calculate the inner product of the quantum states prepared on different platforms. And also, if you want to like directly compare rho and sigma, for example, compute the distance between them, like the square Hilbert-Smith distance, and also there are many other distance that is also has something to do with this inner product. You can see if you want to compute the square Hilbert-Smith distance, then Alice and Bob definitely has to first prepare purity estimation at their own side, and then they have to prepare this distributed inner product estimation using like limited quantum message or classical message, and then they can compute the distance between the states prepared on different platforms. Okay, we have some simple observation. The simple observation is that for purity estimation, if you have two copy measurement, or for distributed inner product estimation, if you have arbitrary quantum communications, then the message is that swap test is all you need. You only need to prepare some circuit like this, do a swap test, and the measurement distributions at the first qubit will be exactly like 1 plus the purity over 2 and 1 minus the purity over 2. So which means that you only need 1 over epsilon square samples is just enough to do both to solve both tasks. And what if we only have classical message, which means that we just don't have quantum message? We will review a result from Anshu, Landau, and Liu in 2022. And to begin with, we just consider some classical analog of this problem. For example, you are given two probability distributions P and Q, and the dimension is just 2 to the n, d equals to 2 to the n. And in quantum case, we want to estimate this inner product trace row sigma, and the classical analog is just to estimate the expected collision number, the sum over PIQI. And the basic idea here is just to use birthday paradox. Alice and Bob just at each side, you just sample n samples from P and Q, and then you compute the collision, the collision operator, which means you just count how many xj equals to yk are there in all the pairs. And by birthday paradox, you can show that when n is equals to theta square root d, which means you can also prove some lower bound. Anyway, this square root d is a tight scaling in the classical case. So if you sample square root d samples from P and Q and calculate the collision estimator, you can just estimate this expected collision number for classical distributions. So what about quantum? Quantum, so for quantum, we just first Alice randomly sample a unitary U, and she sent the classical description of U to Bob. So Alice and Bob both know what this random unitary U is. And they both apply U to each copy at their side. And the third step, Alice measure along the computational basis at her side on the rotated state and obtain a bunch of results. And Bob also measures along computational basis on his side on the rotated quantum states and obtain another bunch of results. And finally, they compute the collision number between A and B. And this is shown that like the maximal in 1 over epsilon square and square root d over epsilon copies of samples are sufficient and necessary. And how about purity estimation with single copy measurement? Well, it's just a direct extension. We can just make rho equals to sigma. I mean, like purity estimation is a local task, but we can just use this protocol above. Like we can divide all the samples into 2 parts and regard rho and just regard it as the case for rho equals to sigma. And you can use like the same numbers of single copy measurement to estimate purity. But I should mention here is that for inner product estimation, they have shown that this bound is tight. But for purity estimation, we don't know whether this bound is tight. Okay, so this just, yeah, sure, go ahead.
Sorry, this is for arbitrary states, rho and sigma, not some special states like pure states or something?
No, this is for general rho and sigma.
Okay, thanks.
Okay, this raises the first natural question is, what if we have only limited quantum communication? And okay, just now we review some previous result on the inner product estimation side, and now we also review some result on purity estimation side. So there are some results. So the previous result is not on purity estimation, but it's on a weaker version, purity testing, which is a distinguishing problem I just mentioned like very early. So you are given a state, it's either hard random pure state or it's maximal mix, and you want to tell which case it is. So obviously this test can be solved if you have a purity estimation algorithm to constant accuracy, because for pure state, you just have purity 1, and for maximal mix, you have purity 1 over d. And it is shown in our previous work that the sample complexity for purity test with k-qubits of quantum memory is the minimal value in square root of d and 2 to the n minus k. So you can see there's a transition. There's a transition at some point, which means when k is equal to n over 2, it's a transition point. If you have fewer than n over 2 quantum memory, qubits of quantum memory, then the optimal protocol is just to do single copy measurement, and you can get square root of d sample complexity. And you have if we have more than n over 2 qubits of quantum memory, you can do better than single copy measurement. And if you have n qubits of quantum memory, you can do swap test. But different from purity testing, purity estimation, we also have to consider the dependence in epsilon. Okay, so now our work just give answers to the 2 questions we just raised. But before going to our results, we have to say something more about the connection between these 2 works. Up to now, it just looks like inner product estimation and purity are two tests that has nothing to do. But it actually they have something to do. So we start with purity test with k-qubits of quantum memory, just as we mentioned at the beginning of this talk. The protocol is just like Alice. It's just like you get a first copy of rho, and you perform some measurement on the n working qubits and k qubits of quantum memory, and then you write some data to the quantum memory, and you get another copy of rho, and you make another measurement. And actually, we can regard the first measurement to be prepared to be performed by Alice, and the second performed by Bob. And this is just very similar to distributed inner product estimation with k qubits of one-way communication, which means like Alice have a state rho, and she can perform. Okay, she can write some k qubits of she can write k qubits of information as the quantum message that she sent to Bob, and Bob then make the second measurement. So for inner product estimation, Alice and Bob can have different rho and sigma, while for purity estimation, they have the same rho. So this just means, I mean, that like these two stuff are equivalent, except for inner product estimation, you have different rho and sigma. So this means if we have an upper bound for distributed inner product estimation with k qubit of one-way quantum communication per copy, then we immediately have an upper bound for purity estimation with k qubit of quantum memory. On the other hand, if we have a lower bound for purity estimation with bounded quantum memory, then we can also show a lower bound in the distributed inner product estimation case. Okay, so our first result is on the upper bound. We show that there is an algorithm for distributed inner product estimation that use k qubits of one-way quantum communication with sample complexity of this form. Well, it's a little bit complicated, but we just recall this 2 to the n minus k and square root d is just what we prove for purity testing. And here we can just regard for 2 to the n minus k, we have a 1 over epsilon square scaling. And for the square root d, we have a 1 over epsilon scaling, just similar to the collision estimator case. And this max is just so you can just regard this part max as the sample complexity for single copy for distributed inner product without quantum communication. And this part is what you can achieve using quantum communication. So the general idea for the strategy here is when k equals to 0, and then just as what we reviewed in the previous work, we can just compute the collision number in random basis, and this gives you this term, the second term. And when k equals to n, you do swap test, and this gives you 1 over epsilon square. And when k is smaller than n, our idea is to use a partial swap test plus a partial collision number in random basis, and this gives you the first term, 2 to the n minus k over epsilon square. So it's natural to ask whether this epsilon dependence is optimal. Unfortunately, although we believe it should be optimal, but we are not able to prove it is the general case. So we show that the sample complexity for purity estimation using k qubits of quantum memory is at least as something like this. It's the same bound with the previous upper bound, except here there's a square root epsilon gap. But we can also observe, just like purity testing, we can also observe there's a transition. When k is smaller than n over 2, which means you have a little quantum memory, then you will have no improvement over single copy measurement. And although we cannot close this square root epsilon gap in the general case, we try to close it for purity estimation if the protocol is using an identical single copy PVM, then we can prove this lower bound like square root of d over epsilon. So this is tight, but it's just for identical single copy PVM. So like how to close this gap on square root of epsilon remains an open question. And actually, I should say it is also an open question in many similar problems and many similar works. Okay, now we go into some technical overview. So for the upper bound, how we get this upper bound? Just as I mentioned, it's a partial swap test plus collision number. We can just think Alice and Bob have rho and sigma at their side. They prepare one copy of rho and sigma. And we divide these 2n qubits into 3 parts. The first part is the first k qubit of each copy. And for this part, Alice just sent her first k-qubits to Bob. And then they perform a swap test. Swap test is just an observable, it's just a POVM in this spaces. And they obtain the output Z1 to Zn on their n copies, on their n samples. And then Alice and Bob both has an n minus k qubit remaining part. And this is B and C. And then you just perform, Alice and Bob just choose some hard random unitary on B and C. And they perform the same U on B and C. And then they measure the rotated state in computational basis. And they get outcome X at Alice side and Y on Bob's side for C. And finally, they just calculate this estimator. So this estimator is just when swap test gives you 0, it's just like swap test give you 0, and you compute the and when xi equals to yi, you add 1 to the estimator, and when the swap test give you 1, and in this case xi equals to yi, you minus the estimator by 1. So mathematically speaking, if we denote the output S equals to XYZ, so this is just generally all the measurement outcome, and we just the estimator is just written here, and we can show that the average value for the average value for this estimator gives you f plus fk over 2 to the n minus k plus 1. So here f is what we want. It's the trace row sigma, the inner product, and fk is the inner product between the first k-qubit of rho and first k-qubit of sigma. So it's a bias estimator, but Alice and Bob can do, but Alice and Bob can then do some, can only do partial swap tests to first estimate this fk, to estimate this bias, and then they can estimate f, which is the trace row sigma we want. And we can prove that the variance of this estimator as some value like this, and combine these two stuff together, we achieve the sample complexity we claim. I mean, like the computation, the computation is a little bit complicated, but the intuition here is very straightforward. You define this estimator, you calculate the average value, you calculate the variance, and by brute force calculating this stuff, and then you can get the sample complexity. And then let's go to the lower bound. So the lower bound for proving purity estimation here, basically is just to reducing the learning problem into a distinguishing problem. So we just consider a distinguishing problem between two cases. In the first case, you are given a maximum mixed state, I over D. And in this case, the purity is just 1 over D. And in the second case, a rho is chosen from a random ensemble. And this random ensemble is chosen by, you pick a hard random state in a larger Hilbert state space. The dimension of the larger Hilbert space is D over epsilon. And you pick a hard random state in this space. And then you trace out the remaining qubits to obtain a small d dimensional state rho. So it's definitely like you consider an n qubit system, and you first you first pick a n plus log 1 over epsilon qubit system, and then choose a hard random state in this enlarged system, and then you trace out log 1 over epsilon qubits, and you will result in an n qubit state. And you can prove that in this case, the purity of rho rho is larger than epsilon with high probability. So as long as epsilon is larger than 1 over d, then if we have a purity estimation algorithm, we can distinguish between these two cases. So the template for proving lower bound for this distinguishing problem is the so-called learning tree. If we consider an adaptive algorithm with t rounds of measurements, like for each round of measurement, you are just doing the 2-copy measurement with bounded quantum memory we introduced before. So it's like in the first round, you prepare 2 copies of rho, and then you measure them using the measurement with limited quantum memory, and you can get different outputs. Because the protocol is adaptive, so based on different output, you get you will choose different measurement in the next round. For example, if you get result S1, then you will choose a different measurement M2 in the next round. But if you have if you get the different measurement, different output S1 prime in the first round, then you will choose a different measurement in the next round, and this will just result in a tree. And the probability of getting into this node, this is the root node, is exactly 1 because you will always start with the first round. But the probability of getting to this node is not 1 because it depends on the probability of getting S1 based on the measurement you perform in the first round. So you have a smaller probability of getting into this node, and then you have a even smaller probability of getting to the child node of this node. And finally, you will have after T rounds, you will get a tree of depth T. And for each leaves, you will have some probability of getting into this getting to this leaves. And this will result in a probability distribution on all the leaves. And the necessary condition for you to distinguish between between these two cases is that the probability distribution for these two cases on the leaves are far enough from each other, which means the TB distance between P and Q corresponding to the two cases on the leaves are at least θ1 from each other. Okay, so let's consider exactly this hard instance. So for this hard instance, we just denote the probability distributions on leaves L, so on some leaves L, as P psi L for the second case and P rho ML for the first case. And we define the likelihood ratio for getting to a leaf L here. It's just a ratio between the second case and the first case of getting to a particular leaf L. And similarly, we can also define the likelihood ratio for getting an outcome S for a particular measurement. And it's just the likelihood ratio between the second case and the first case. And as I mentioned, the necessary condition to distinguish between these two cases is that the probability distributions on the leaves are far from each other. And this TB distance bound can be reduced to a one-side TB distance bound, which means, so this is what we want. This is what we want previously. We want to show that the TB distance between the second case probability distribution for the second case on the leaves average over all the random chosen psi, and the probability distribution for the first case is θ1. And we can further write this TB distance to be the proportion of the likelihood ratio that is smaller than beta plus 1 minus beta. And the next step is to show through a martingale argument, showing that this probability is bounded. Like, for example, if we choose beta to be 0.9, then we want this. Then the next step will be to bound this probability of small likelihood ratio to be smaller than 0.1 plus the depth of the tree times some value related to the likelihood ratio for each single measurement. And final step, we will compute a bound for each step for the likelihood ratio for the second moment of the likelihood ratio for each single measurement. So if for example, if we can show this value is small, then if we want the total variance distance here to be large, we want this probability to be large. We want this probability to be large, then we will need T times this value to be large. And this will require a very deep T. Okay, so that's the workflow of how to prove the lower bound in this case. But like how to calculate this bound is also some kind of like brute force calculation, and yeah, and you can refer to the paper for details. Okay, so like for this story, I also want to mention some concurrent results to make the story more to add more stuff on the story. Like concurrent to our work, Srinivasan and his collaborators also have some related results. They show that if you only consider rho and sigma are pure states, and if you consider like k-qubits, Alice and Bob can have k-qubits of quantum communication in total, not per copy like we do. Then they show that 2 to the m minus k over 2 copies are sufficient and necessary. And they also consider another problem, like you want not only distributed inner product estimation, they also consider the problem of distributed function estimation for some psi m5 for some observable m. And in that case, if you assume Alice and Bob only have classical estimation, then they also prove some upper bound and lower bound. And there's also a quadratic gap in epsilon dependence, like what we met in our work. Okay, so now like let's give you some take-home message. Okay, the first message is that the motivation for purity and inner product estimation. So on the one hand, we can show some information theoretical quantum advantage for learning quantum data quantumly, and also these tasks themselves are key subroutines for benchmarking near-term device. Like purity, you want to benchmark your quantum computer locally. Inner product estimation, you want to benchmark states on different on different platforms. And a second message is that we show there's a connection between estimating purity with limited quantum memory and distributing inner product estimation with limited one-way quantum communication. And the third one is the transition in the sample complexity we prove. There's a n/2 transition point. And if we have fewer than n/2 quantum memory, then unentangled measurement or single copy measurement is just optimal. And finally, as an open question, there's still a quadratic gap in epsilon dependence in a series of, in not only our work, but a series of related works. Okay, I think that's all for this talk, and thank you for listening.
Okay, thank you very much for giving a wonderful, informative talk. Okay, so now we have plenty of time. Yeah, more like 10 minutes for questions. So yeah, if you have any questions, feel free to unmute yourself and to ask them now.
Hello, I have a question regarding when you prove the inner product estimation. You say you select k-qubit to do swap test, and then you do randomized measurement on the n minus k-qubit.
Yeah.
And if I understand right, the randomized measurement, you use hair random.
Yeah.
Would the result be different if you choose the Clifford random gates? That's similar to what classical shadow does.
Yeah, I think so here for, let's see, for average value, I think you need 2 design here. Like not necessarily hard random, but you need 2 design. But if you compute the variance, you will need 4 design. Like Clifford circuit is not 4 design. So I guess Clifford, you cannot use random Clifford. But as long as you have like random 4 design, that's enough.
Okay.
So related to this, so in your protocol, you choose just the first k qubits. You don't really do any kind of processing beforehand.
Yeah.
So have you guys thought about, maybe, I mean, presumably Alice and Bob on their system, they could do full tomography on their state and even diagonalize and do all sorts of stuff. So have you guys thought about ways of applying a easy to describe unitary to transform the state so that the first k qubits are the most useful qubits to do swap test on, and then sending a description of that easy to describe unitary to the other person?
I think like okay. So for the first k qubit, it's not like it should be the first k qubit. It's just like you can choose any k qubit. You can also choose the last k qubit.
You could also choose, you could also choose k qubits after you've done some unitary on the system, right? And those k qubits could be much more contain much more information about the overlap.
Yeah, but if you want to do state tomography, you will need d square samples. But this test in total, you only need square root of d samples. that's much cheaper than state tomography. And
Yes.
actually, like in this setting, you can only do like single copy measurement or like slightly more than single copy measurement. I think there's a reason. So it is known that if you can only do single copy measurement, then state tomography will need d-cube samples. And even if you can do like 2 copy measurement, it's still like d-cube samples is necessary. So it's like you will first have to use d-cube copies to do state tomography and then decide which k-qubit. But in our protocol, you just arbitrarily choose k-qubit, and in total the sample complexity is just square root of d over epsilon, or even like 2 to the m minus k over epsilon square. So that's much fewer than state tomography. State tomography is really expensive.
Yeah, I mean, I guess state tomography was a stand-in for the variety of techniques you could use. You could use normal tomography or whatever, but obviously each choice has consequences on the quality of information you can get out. But yeah.
Yeah, but your point is interesting because, like, I think, okay, so why we don't need this in our setting is because we assume you have k-qubits for each copy pair, and for this case, we already show that if you only consider the n dependence and the k dependence, it is tight. You can prove the lower bound. But I think for the case, like if you have very restricted quantum communication, like you in total only have k-qubits, it might be possible to, like, you first do some techniques on your own side to figure out which k-qubits like decide the most information on your copy, and then like transfer this k-qubits. It might be possible to help, but I don't know. Yeah.
So can you just remind me again? There was a lot of different countings and restrictions on the thing. So you're counting the number of copies, but so you have a restriction on or your sample complexities in terms of the number of copies, but then you have a restriction on the communication. So there's like potentially another regime where your complexity is measured in the amount of communication, and you're free to do anything you like on either side.
So what's your
So my question is that regime kind of studied, or is there a I guess that's just the communication complexity, like one-way communication complexity of inner product estimation. Okay, so never mind. I'm just trying to.
Yeah, it's just like you fix the communication complexity, and you want to bound the sample complexity. So we fix the communication complexity to be k times the total, k times the number of copy pairs, and you want to characterize the sample complexity in this case.
I have a question regarding this slide. When we mentioned, you mentioned that the choice of k-qubit is arbitrary, but does it have to be consecutive qubit? Can I choose like random? Yeah,
I
they
think
have
like
to be consecutive.
You can just arbitrarily choose k-qubits in n-qubit. Then they don't need to be, they don't actually need to be like consecutive k-qubits.
So okay, so it's really arbitrary. Any. They need okay.
Any k in. Because the like presentation, like the expression here will not change. You just change the k-qubit you are acting on, but it's still like swap k tensor something.
Yeah, I see.
And you will get the same result here and get the same result here. So the sample complexity will not change at all.
It doesn't affect the randomized measurement later, right? Because in the second part you need to do randomized measurement on the n minus k qubit.
Yeah,
and they don't have to be consecutive either.
Yeah.
Let's see.
Sort of just a simple question related also to this. So if you're restricted to pure raw in sigma, is there an improvement that you can achieve, or it will just get the same?
I think what we know is like the concurrent work, where they show k-qubit communication in total, they show this bound. But
oh yeah, because they're already doing it.
Yeah, but in our case, like whether we can get improvement for, okay, let me see. Yeah, that's a good question because here we argue that the lower bound for purity estimation work for distributed inner product estimation, and the upper bound for distributed inner product estimation work for purity estimation. So it's like so the lower bound we prove is for purity estimation, and in this case, like if you make rho to be pure state, then this lower bound will never make sense, right?
Yes.
So it is completely possible if you assume rho and sigma are pure state, and you can improve upon this upper bound. It's possible.
All right. Yeah. So yeah, I guess like, is there anyone else who have questions?
Just a very strange question. So if either Alice or Bob have more copy on their side and in your setting, and will that help?
That's a good question. Let me think about this. Oh, yeah, more copies on their side. So, like, what kind of more do we have? So okay. What? I tend to think you can have very limited improvement because so even if Alice has unlimited number of copies and she can do a precise state tomography and she send what the state is to Bob, I'm not sure what is the sample complexity in this side to estimate. So you have an unknown state, you have a description, and you want to estimate the inner product. Wait, is this problem really, is the complexity for this test really known?
I mean, in that setting, I mean, it depends on what the description is, right? But presumably, imagine if the description is a circuit that prepares that state, then you could undo, like you could apply the inverse of that circuit. Bob could apply the inverse of that circuit and then measure in the computational basis. And now it comes down to measuring the probability of seeing the zero outcome, right? Which is like,
yeah, but that's a pure state case, right? If rho, what if rho is a mixed state? You give a description of a mixed state, arbitrary mixed state, and like, and you want to.
But it reduces to like a classical kind of setting now, right? Where you have to like estimate an entropy type quantity on a classical distribution. Maybe, okay, maybe not precisely true because Bob's state could be not diagonal in this basis, but.
Oh yeah, but I just realized, like in this extreme case, it seems that Bob can use very few samples to estimate because he already know the description of Alice state, and he can just regard this description as to construct some kind of observables, regard rho as an observable, and you can absolutely estimate this. Yeah, it seems that there's a trade-off. Like if you allow more copies at Alice side, it seems that you can have fewer copies at Bob's side. Yeah, so yeah, this can be an open question, like to set up a trade-off between Alice and Bob. Like Alice has more copies, Bob can have fewer copies.
I wonder if there's even going to be like some transition. Oh wait, probably not. Probably will just really scale all the way to infinity, I guess.
Yeah,
hard to say.
I have no idea.
Yeah. yeah, I mean, I guess it is sort of like a really different problem at that point.
Yeah. But I'm wondering if like, so a very naive thought can be Alice can produce as many as some classical shadows of her copies, and she sent the classical shadows to Bob, and Bob then compute the inner product between all these classical shadows and sigma. I'm not sure what is exactly the sample complexity here, but I think this might work in some, at least in some regime.
Yeah, thank you. Yeah, this is an interesting question to explore. Yeah, thank you.
Just on that note, there's, the classical shadows information is like there's lower sample complexity if the state is pure. And so Alice could send, have lower sample complexity in this setting.
I mean, like, to create many classical shadows, I mean, like Alice, like she prepared maybe the scaling of OD classical shadows, and she sent all these classical shadows using classical message to Bob, and Bob and I'm wondering like if Bob can use fewer copies to like compute the inner product. He can just regard like each classical shadow as an observable, and he then do shadow tomography at his side using this classical descriptions of classical shadow. And I'm not sure, but yeah, it might work. And he might only use like polynomial n copies. That's enough. But Alice probably will have to use maybe more than d copies or even more. I don't know.
I think if it's pure, then that's not the case, because yeah, I'd say it might be a lot simpler if it's pure, because like in I work with my collaborators Daniel Greer and Luke Schaefer. We showed that the sample complexity for classical shadows on pure states with joint measurement is scales like a quantity we saw lots of times in your talk. Actually, it's like a minimum, or sorry, the maximum of one epsilon squared. And yeah, so
the classical shadow, right? Single copy,
yeah,
then it should be
yeah.
the minimal in M and dimension. But if you have local observable, if you assume local observables, this can be changed to like 2 to the k. But yeah.
Sorry, I'm not talking about this quantity. I'm talking about there's like this quantity minimum of 1 on epsilon squared, and
oh, I see. Here, right?
yes, except that square root of d is like square root of trace O squared, where O is the operator or the observable. So I'm not sure, but if that observable is like a state, then trace O squared is at most 1.
Yeah.
And so you get a scaling that's like 1 on epsilon squared. That's the sample complexity for estimating expectation values of like to produce shadows. Yeah. So I think you could not scale in D, potentially, that procedure.
Yeah, one side it has no scaling with D. On the other side, you will have more. If you will have to use more copies.